Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to begin the concept of force reduction. And what that really means is, say we have a body, a lot of forces acting on that body. What we essentially want to do is take all those forces and replace them with one single force. It makes the analysis of whatever we're trying to analyze, say a beam, much more simplistic, much easier, especially for a computation. If you're using a computer, it's much more quick. However, as you guys have learned, moving forces is not as simple as it was before because of distances. When you move a force, we're creating moments or taking away moments. So we must account for those moments when we're doing our force reduction. So force reduction goes from really, really simple to really, really complex. And over the next couple videos, I think starting with this one and going all the way up to the 5th video, we're going to take those steps and get more and more complex as we go on. Right now, we're going to start with the simplest case, and it's the force reduction of just some 2D forces. We're going to take a bunch of forces in 2D and convert them to a single force with a corresponding moment. Next video, we move on to 2D. Sorry, we don't move on to 2D. This is 2D. We move on to 3D. And then in 3D, it gets a little bit more complex, as you guys will see. And there's 3 videos for 3D because there's a lot of things we can do for force reduction. It's not just, it may just be more. All right, so looking at this example, it says it wants us to replace the force system acting on the beam by an equivalent force and couple moment at point A. So what that really means is it wants us to take all those forces in black on this beam and create a single force at point A. So we know it'll be some sort of downward force, but basically we want to convert all those forces into a single force at point A along with a moment at point A. So it wants to take all those forces in black and convert it to the forces in red. Just a single force and a single moment. So when we're dealing with force reduction, there's kind of 2 steps we have to deal with. One is we have to find the resultant force of the system. And then the second one is we have to find the moment all those forces created. So in 2D, it's not too bad. And when you're given a beam, the best thing I like to do, and especially for later on, is we're going to want to draw a free body diagram. So it'll become very, very, very important. So let's just draw a quick free body diagram. Remember, it doesn't have to be beautiful. It doesn't have to be crazy. Just something to kind of show where all the forces are, and hopefully it'll help you guys just later on. So we know that in this diagram, I'll draw the forces in red so they stick out quite a bit. We have a force here. We have a force all the way at B going straight up. And we also have another force kind of coming in like this. So as you guys will see, not exactly to scale, and that's fine as long as we get the kind of the general concepts. So we got 2.5 kilonewtons here, we have 1.5 kilonewtons here, and we have 3 kilonewtons at the end. Real quickly, we should add in some other stuff. We know that this point is A, we know that this point is B. We have some angles for our forces that we should probably include to help us solve. So we know that this is 4, 3, and 5. We're given an angle for this force, so we're just going to kind of put this straight up and make the angle to show that this is 30 degrees. So let's put 30 degrees. And finally, for beams, we should always dimension our beams because we're dealing with moments here a lot. It's good to know dimensions so that when we're dealing with the moments, we can find that moment arm that we are going to need. So I know we have 2 meters, we have 4 meters, and we have 2 meters. So this should be kind of review of everything. And what you guys will find is this mostly will be review. Now, here's the problem that students are going to have, is they're going to start assuming that this is an equilibrium question. And it's not. We're dealing with force reduction. Basically, we're going to take all those forces onto my free body diagram in red and convert them to a force. In these type of questions, we are not summing the forces are equal to 0. Because if we look at these 3 forces real quick, just off the bat, and we sum the forces in y, we see that all those forces are going downwards. They're all negative forces. So there's no way that this, when we sum the forces just for those forces, it's not going to be an equilibrium. But of course, we know that at A, there is a roller, so this will have a reaction force that would be going upwards like this. And then the same thing at B with the pin would also have a reaction force. So because of those reaction forces, we can use equilibrium to solve for them. However, when we're dealing with force reduction, that's not our interest. We're not going to worry about those reaction forces. The only thing we're worried about is getting those red forces into just one single force. So let's just label that on the diagram real quick. Actually, we'll do that after because we don't know the directions of the force yet, so it's probably not the best. So the first step is you want to get a resultant force. And this is kind of the easy step because all we're going to do is take all of those forces that are on the beam and add them together. So in 2D, we know it's just adding the components, very simple. In 3D, well, same thing. We're just going to be adding those components. It should be really, really simple. So I'm just going to go with the summation of the forces in X. And remember, I'm not doing equilibrium here, so I'm not including those reaction forces. I'm just summing those forces that I want to create into a single force. So starting, we'll go from left to right. So we know that there's 2.5 kilonewtons, and I'm putting negative because we know it's downwards. And we know it has a horizontal component of 4/5. All right. Oh, and sorry, going downwards, I'm thinking of the wrong thing because it's going to the left. We're summing the forces in the x direction right now, not the vertical direction. So I got a bit ahead of myself. And then we have a second force due to the 1.5 kilonewtons. And we know it's positive because it's going to the right. And we know its component will be the sine of 30 degrees. So remember, this is an equilibrium. I'm not going to put equals 0 here because these forces by themselves will not cause equilibrium. However, when I put these two in, what I get is I get my summation of forces due to those external forces as negative 1.25 kilonewtons. So it basically means the summation of all the forces in the x direction, or the external forces, is 1.5 kilonewtons to the left. And we're going to do the same thing real quick with some of the forces in the y direction. Remember, these are just the external forces. I'm not including any reaction forces. And we know this can be negative 2.5. And all the forces will be negative because we see that they're all going in a downward direction. And the component's going to be 3 over 5. And then minus 1.5 times the sine. Oops, sorry, it's not the sine. It'll be the cosine of 30. So cosine of 30. And then, of course, we have that single force all by itself, which is the minus 3. And while we find this is equal to negative 5.80 kilonewtons, or 5.8 kilonewtons downwards. So we have the components of our force, but that's not exactly what we want because those are still two forces. We have a force in the x, force in the y, but we want a single resultant force. We don't want two components. We want that single resultant force. So we know that we can actually find that resultant force just through simple trig. So we know that the magnitude of the resultant force will be the square root of 1.25 squared, so the x component, plus the square root of the y component, so 5.80 squared. And what happens when I throw all of that in, I'm just going to finish that square root sign, is I get 5.93 kilonewtons. So that's the magnitude of that force. However, it's just a magnitude. We have no idea which direction it's going. We don't know if it's going up, going down. So that's the next thing that we're going to want to solve for is just its direction. So the next thing we do is we go theta is equal to the tangent, or the inverse tangent. And we're going to go the y over x. So it's going to be 5.8 divided by 1.25. Let's close the bracket here. And if we do that, we should get 77.8 degrees. Now, this is very important because a lot of people assume that this theta is always measured like this. However, that's incorrect. And we can solve that very easily and know it's incorrect because just the signs of our forces. So if we look in the x direction, our force is going to the left. So it's going something like this. And if we look in our y direction, it's negative 2, so we know that this one's going down something like this. So we know that our resultant force must do something like this. Thus, that's 77.8 degrees. That's this right there. And that's the theta. So the best way to denote this in here is it's going to be something like this. Alright, so I'm just going to erase this real quick so we can move on. So right now, we're done step one. We have our resultant force. But remember, forces when there's distances involved, they create moments. So we must account for that moment. However, this is really, really nice because all we're going to do to get that moment at A is the same thing as we did for the forces. We're just going to add up all the moments caused by those forces on point A, and that's our moment at point A. So all we have to do is go sum of the moments. And remember, this is at point A, and that's going to equal 2. And before we kind of go a little bit further, let's just take a look real quick. We see that they don't give us a thickness of the beam. So what that means is all the horizontal components of these forces, they run through A. For example, the 2.5 kilonewtons, it's pretty obvious to see. It's going to have a horizontal force of something like that. But if we draw its line of action, we see that it's going to hit right at point A. Thus, we know it will not create any moment because that distance will be 0. So I'm just going to get rid of this force real quick. So the only thing we have to worry about in this case is the moments caused by the vertical forces. So we're just going to go left to right real quick. So we know that the first one we have is the 2.5 kilonewtons. So 2.5, and we know that its vertical component is 3/5. So we're going to have times by 3/5. And we're going to have to find a moment arm for this. So that's that perpendicular distance. And we can see that that's going to be 2 meters. So we're just going to put a 2 here. And last thing that we have to check, of course, is the direction of that moment. And if you look at that vertical component, we're going to see that it's going to create a clockwise rotation about point A. So if it's clockwise rotation, this is going to be a negative moment. And what you'll see is the remaining forces, they're very similar to the 2.5 in that they also create a clockwise rotation about point A. So we know for the rest of the moments, we're just going to have negative signs. So it's going to be minus 1.5. And again, we want that vertical component. So it's going to be times cosine of 30. And then times the moment arm. So in this case, we're going to have to take that 2 meters and add 4 meters. So the moment arm in this case will be the 6 meters. So we're just going to go 2 plus 4. So that's the moment arm in this case, that perpendicular distance. And finally, we have that third component due to the 3 kilonewtons. And for its component, it's going to be 2 meters plus the 4 meters plus 2 meters. And if you throw all that together, what you'll get is a moment of negative 37.8. And the units are kilonewtons times meters. But let's go back real quick. I know that some of you may be, okay, where is he getting the moment arms from? So remember, we're dealing with perpendicular distances for moment arms. So let's go to green. I want to take this moment about point A right there. And I'm looking at the 3 kilonewtons all the way at the other side, which we know acts in this direction. To find the moment arm, what you're going to want to do is find the perpendicular distance. So if my force is going vertical, my moment arm must be horizontal because we're dealing with perpendicular distances. So the moment arm for this case will be A all the way to the other side. And if we take this distance here, we see that it's going to be the 2 meters plus the 4 meters plus the 2 meters, which is what we have right down here. So now we have that moment of A due to the forces. So what we can do is our new free body diagram, if we wanted to, is we can draw it across. We know that there's a roller at A. We know that there's a pin over at B. So let's just label these B. This is A. What we can also do is label the distances across the beam. So you do something, say, like this. Again, it's not to scale, which is fine because it's clear. Yeah, as long as it's clear, it's fine. But remember, we took all those forces that were across the beam and converted them into 2 forces. So let's just look at this real quick. We see that we have a force of 5.93 kilonewtons. And we know that that's going down and to the left. So at A here, we have a force that kind of goes like this. Right here. And we know that this is 5.93 kilonewtons. So notice how I didn't put negative because I actually show the explicit direction of the force. And real quick, it's also good to just throw in angles so people know exactly how much we're dealing with. So we know that this is 77.8 degrees. And then the last thing, of course, we have to include is our moment that this creates. So we know that it's negative 37.8, and we know that what a negative moment means is it's going clockwise. So in this diagram, we're going to draw a clockwise rotation like this, and we can put that this is 37.8 kilonewtons times meters. And that's it. As you see, this is the simplest case. We have three forces in red, and we convert it into a single force and a single moment now in blue. And that's it. So for 2D, it's not bad. As you guys will see later on in the course, we'll do this a lot, converting forces. And it's not so much as just for fun. This will save you a lot of time. And later on in life, it'll save you computation time, which you'll learn to cherish very, very dearly. There's nothing worse than waiting 3 hours for some results to come back, especially when the results turn out to be wrong and you're going to have to modify something small and rerun it and waste 3 more hours, stuff like that. So this is why we do this. Again, this is the simple case. This is the nice, easygoing case. The next example, what we're going to do is we're going to take our concepts from 2 dimensions and apply them to 3 dimensions. So we're going to have a bunch of forces in 3D, and we're going to convert them into a single force in 3D and a single moment in 3D. So stick around for the next example. So thank you all so much for listening. I will see you guys in the next video.